Hello and welcome to Differential Equations Review. This is going to be a review of Calculus 2 concepts needed for differential equations for chapters 7 and 8, chapters on Laplace transforms and power series. So in differential equations we learned a whole bunch of ways to solve differential equations, and two probably most powerful ways to solve differential equations are in chapter 7 and 8, which is Laplace transform, right? One of them is Laplace and the other one is power series solutions. So we are going to fill in the blanks of the things that we are supposed to use, and the topics which I listed in your on Canvas under the when I sent the announcement for this, I said that there's going to be a Usub. Well, Usub is actually Calculus 1 concept, and that's just the integration technique that is very useful and very, very frequent because it's backwards chain rule. So Usub is something that does show up, but it's not major. So if you remember, let's say having xe to the x squared dx, you would set u to be x squared, and then du would be 2x dx. Since you need to fix the 2, you will put 2.5 in front to fix the constant, and you will get your 1/2 integral. Now 2x dx is your du, and you have e to the u. This is actually transformation. And transformations are those mathematical manipulations that you use to change the domain from one type of the domain to another type of the domain. In this case, your x domain switched into a u domain. And when you made that switch in a domain, it's actually has to do something with spaces in mathematics and so on. We transformed our problem from this very complicated problem into a very simple problem, which we can now simply solve by just integrating e to the u, and then we bring x back into the picture, right, plus c. We transform this back. Now, the transformation here is very easy. It's very direct, right? We just have this correspondence that u is equal x squared, and it's very easy to go with this transformation forward or backwards because it's literally just swapping. Now, one of those ideas in the Usub is what they call a back U substitution, back Usub, which would be found in a problem like this, for instance, right? So you have this problem, and now you can distribute, you can do pretty much any of these things that you are used to seeing in other previous examples. Therefore, right, we have to use the Usub, and when you go with the Usub here of u equals x minus 1, then your du becomes dx. And when you do this substitution, what happens is that you still have this x in here. You have a square root of u du. So this x is a problem. And this x is actually taken care of by going to the substitution and solving for x to get u plus 1. It's a very unique trick, not used too much. But now, when you take a look at this problem, it becomes easy because you can now u to the 3/2 plus u to the 1/2 when you distribute the square root of u, and now the problem becomes easy to solve. So this problem, again, not very frequent, shows up here and there, but it shows you that you also have this option of playing with the actual substitution, which is transformation, to replace any lingering parts. So this is 2/5 x minus 1 to the 5/2 plus 2/3, again x minus 1 to the 3/2 plus c. So that was a little review of what we know as Usub and back Usub, just in case it shows up here and there, but again, it should be the basic technique. Now we go with the heavy hitters. Integration by parts. We have already seen integration by parts in 7.1, where we did the forward Laplace transform. So integration by parts is the formula which you can also visually derive, but generally people just memorize it. U dv is equal to uv minus integral of v du. And if you want to see where the formula comes from, I mean, it's backwards product rule, but the much easier way is to just take a look at the function with uv like this, and then you just draw this rectangle. So if you take a look at this rectangle, the area of this rectangle is u times v, right? And then each one of these integrals, right? This integral over here is v du, and this integral over here is u dv. And when you add them, you get this, and you just rearrange the formula. So it's very simple to come up with this. I'm going to erase this because this is a kind of verification, proof, whatever. We are focusing on the formula. You can just go back in a YouTube video and just watch that little part if you're interested. Now, this forward, the integration by parts is used in every forward Laplace transform that you have to do. And you've seen that Laplace transform of some function f of t was given as the integral, right, that went to e to the negative st times f of t dt, and that was it was going to infinity. So there are a couple of these very important features that we have for this particular transform, but the most important part is that you have this multiplication of two separate functions here, right, which you can use in your udv format. You can attach, let's say, ft dt or whatever is working there for you. So now, if you, let's say, want to transform, one of your problems, right, you can quickly figure out integration by parts. So integration by parts is done on, let's go like this. Integration by parts is done, let's say, integral of x cosine x dx. Right, this is one of the basic introductory. Let's go cosine 3x just because we can. One of the basic introductory examples. Now, you do see multiplication between these, and you immediately go and say, all right, I'm going to set up my integration by parts where I have my u to be x, and I want u to be x because once I do integration by parts, the derivative is going to kill it, and then the next integral will not have this polynomial piece, which is what made this problem difficult and the problem. And the rest we're going to stuff into the dv, right? So dv part has to contain the dx part because that's the side that you will integrate. So now you find the du by derivative, right, differentiation, and v by integration. Integral of cosine is sine 3x, except it will be divided by 3 now. And we don't have to put plus c here because there will be a plus c and the entire problem later on. Now, I like to put this arrow, and you will see me put this arrow every time, because this arrow literally shows me the formula up there. You see how it goes U times V, right, for this part of the arrow, and then you have a V du for the horizontal part of the arrow. So it kind of shows me, right, that I will not be using this part at all in my formula, which is right here, and I just need to compile that piece and go from there. So once I have this piece, I just put the formula together, and it becomes 1/3 x sine 3x minus the integral of sine 3x over 3 dx, which is now, again, another basic integral. When we kick 1/3 outside, we can solve this. So now it's easy. So integration by parts is the method that will be used for all of your, or most of your, forward transforms. So when you have t squared, or a constant only, and even though with those sines and cosines, with the exception of e, right? I did that one in class. We did not use Usub. It was a basic integration, and also depending on, right, how much you learned in your Kalk2 class, thinking, let's say, hyperbolic functions. I have seen students, struggle through calculations like Laplace transform of, let's say, sine hyperbolic x, right? That's a formula on the cover of your book, right? But how do we get this? And then students would say, okay, well, that's just the integral 0 to infinity of e to the negative st. Oh, this was supposed to be a t over here, sine hyperbolic t. And then sine hyperbolic t dt, and go to the Usub part, which is, again, you have to do it twice. It is as evil and complicated as if you were just using the regular sign, because also hyperbolic functions are cyclic in their derivatives and integrals, just like trig functions are, without being periodic, which is really amazing. But as I said, if you have enough knowledge of calculus 2 and hyperbolic functions, you can bypass the calculation using double integration by parts and all of those tricks and things, and just write your sine hyperbolic in terms of their E definition, right? So you'll have your limit b goes to infinity, right, 0 to b, and now e to the negative st, your sine hyperbolic is written as e to the t minus e to the minus t over 2 dt. And this, right, really eliminates your integration by parts, because you can distribute now this e, and you can kick the half all the way in front of the limit, and it becomes a joke of the integral, which eliminates eliminates other calculations. So when I kick 1/2 outside, that's done. And now I'm going to have e to the negative st plus t minus e to the negative st minus t. All of that in parentheses dt. And you can clearly factor out t, and it just becomes a very basic calculus 1 integral like e to the t, right? So when I kick out negative t over here, so I kick out negative t, I have e, and then I have s minus 1, and then negative t, and then minus e, and when I kick out negative, I get s plus 1, and then t, and dt. So you see that this is already taking a shape of basic e to the at formula, whose integral is e to the at over a, which a is this whole piece with a minus minus parenthesis and minus other parenthesis. Those are your a's from the basic e formula. So we are able to, right, when we have extra knowledge of these things, which is your, think chapter 7 or whatever you learned in Kalk2, hyperbolic functions, maybe it was chapter 6, chapter 7, it was at the end of one of those chapters. You learn about hyperbolic functions, and then this feature, like the sine function, is there. And I'm just trying to find where, maybe it's 7.3. Yes, 7.3 in calculus textbook. You can learn about hyperbolic functions, and once you have this integral, I mean, now you're done, right? You avoided integration by parts, but you can only do that for hyperbolics and e's. You can also do it with sines and cosines, but that produces another issue because sine and cosine go with the complex numbers in exponential functions. I'll write that down for you as well, but these guys are the ones that are easy. So you have e to the negative s minus 1 t divided by minus s minus 1. And then you have minus, again, e to the minus s plus 1 t, using this formula, divided by negative s plus 1, like this. And then this is computed right from 0 to b. So again, easy. We did not have to use our integration by parts. We were able to very quickly deal with exponentials. So once you know your hyperbolics, and maybe you know some of the differential equations are going to be tied now into this, you have your sine hyperbolic x given as e to the x minus e to the minus x over 2, and your cosine hyperbolic x is equal to e to the x plus e to the minus x over 2. Now when you compare that to sine x being e to the I x minus e to the negative I x over 2i, and cosine x being e to the I x plus e to the negative I x over 2, no I in this case, right? You see how similar these formulas are, and this is the way actually Euler got them in the first place. He said, well, what happens if I just erase these i's, right, from sine formula? And then he worked out all of the properties of what he got and said, well, let's call them hyperbolic sines and cosines. Right, they're close, but they're not exactly there. So you could bypass integration by parts by plugging this into your Laplace, but then the question is if you know how to convert it back into the real, right, at the end. So maybe, you know, for that stuff you do integration by parts, but you can definitely cheat it off on this one, and you're supposed to. I mean, if you have the knowledge for it, right, go ahead. So that was integration by parts, and as I said, we use it in a forward Laplace. We have already seen it in class a couple of times. So you know, for more exercises and problems, you should definitely watch Kalk2 lectures. I mean, for any of these, if you discover tonight that you have a problem with it, because you do not want to see any of these things for the first time on the exam, especially the only exam you see this on is final. So you do not want to see, you know, 40% of your exam for the first time and go, what the hell is this? That's the part, right, that is a concern. Partial fraction decomposition, finally. Again, if you have any questions, make sure you are asking along the way. It's okay to interrupt and ask, because this is review for you. I don't need this, right? I know it. All right. So partial fraction decomposition is designed to take a single rational function and break it over a couple of rational functions. Therefore, decomposition, right? So if you think about what we are doing here, is we're going to take something that is, I don't know, 3x minus 4 divided by x plus 3x minus 1, and we're going to break that into two fractions that will have these factors as denominators. And our job is to figure out what are a and b, right, on top. Now, why do you want that? Well, you want that because each one of these, when you do the inverse Laplace, right, when you do inverse Laplace over here, inverse Laplace of a over x plus 3 is going to be, if you paid attention, right, a e to the negative 3t. Right? So all I need to do is to work out my partial fraction decomposition to actually figure out what a is. What's that number? I don't have this in my inverse Laplace or forward Laplace tables. So when I get something like this as my solution in the frequency domain, I need to break it apart into these small chunks that will make sense. So for partial fraction decomposition, we have the 4 setup cases that you need to know, and if you know those 4 setup cases, you will be able to set up any partial fraction decomposition that you run into. Now, guys, this is only for polynomials, right? If you have a trig function floating about over here or something, well, it's not partial fraction decomposition. Partial fraction decomposition is only for both of these being polynomials, which is what creates a rational function. All right, so what are the 4 cases that you have to memorize? Now, I usually write blah over x minus c. This is called linear, right? And the setup for that is a over x minus c. So you will just put, when you're writing the setup, you will just put a on that term, which is actually what I have here. You can see that both of these are linears. So both of these are case 1s. So here is my a over x plus 3 and a over x minus 1. But since a was already used up, I'm using now b. But technically, both of these are a over x minus c. It's the form that you are supposed to remember. And then you just use whatever variables are available to you. The next one over here is blah over x minus c squared, which is repeated linear. And that one will have a over x minus c plus b over x minus c squared. Now we are going to do examples of this so you guys can see not just the setup but also the calculation, even though we already did 2 or 3 in class. Case number 3 is going to be blah over prime quadratic. Prime means cannot be prime quadratic cannot be factored, right? Because if you could factor this into these guys, well, then you would just have linears, right? So not each one of these can be factored. Some of them are prime. And the setup there is ax plus b divided by this ax squared plus bx plus c. And the last one is blah over ax squared plus bx plus c, everything squared, which is repeated prime quadratic. And that one is ax plus b over ax squared plus bx plus c plus cx plus d over ax squared plus bx plus c, everything squared. Now at this point, right, you will look at these formulas and try to find these similarities, right, and the way they're connected to each other. Like, you can see that first and the third are like the base cases, and then the repeated ones, and then look how they repeat with a square on the other one. I'm just gonna go grab a bottle of water because my throat is killing me. Just 1 second. Look at the formulas. All right, let's take a look at examples with partial fractions. Now that is in chapter 8. Now let's go with two different things. One is setup. So learn setup. Let's say you have 4x plus 1 divided by x squared plus 2x, right? It's your job to factor this into 4x plus 1 over x plus 2, which gives you a over x plus b over x plus 2, which are two linear, right? 2 case 1. Now, there's a way to solve this, obviously, but I'm just talking about a setup. Let's say you have 3x minus 1 over x cubed plus 4x. So 3x minus 1 is x squared plus 4. Now what you have is a linear plus the quadratic, which cannot be, right, it's a prime quadratic, right? Remember, you can factor x squared minus 4. Someone is chewing into the microphone. It's going into the recording, so anyway, x squared minus 4 can be factored, right? But the plus one cannot over real numbers. You have to put complex i's, right? 2i and negative 2i would be good. So when you have a prime like this, observe that that's a quadratic, therefore it gets a quadratic. This is your case 3. Right, so case 3 in the setup. Now, is something like this going to be in your inverse Laplace? Well, hell yes, right? Because if you think about it, your denominator is that s squared plus k squared. Now look at your numerator. It's bs plus c. And if you split this, you get b s over s squared plus k squared plus c over k, over 1 s squared plus k squared. Yeah, they're your, this one and this one. Well, this needs to be fixed into k, so you will fix that k and put c over k. But we'll learn that in the differential equations. But your partial fraction decomposition leads you into hyperbolic sine and hyperbolic cosine when you split this partial fraction, right? So these things appear in every problem. This is not something that, oh, it will show up once. It shows up in almost every problem because your answers are either trig or hyperbolics, right? So we need to know, right, correct ways to set this up and compute them eventually. All right, so now I'm going to get rid of this stuff because, again, this is DifEqs. We are learning or reviewing whatever partial fraction decomposition. Now, how do we solve these, right? So anytime when you get these partial fraction decomposition, you already have your target denominator right here. So you multiply what's missing from that denominator into each one of these. And that creates equation that you use to do partial fraction decomposition. Now, obviously, for details, you can go and watch full partial fraction decomposition lecture where all of this is outlined in the greatest detail. So now you have your a x squared plus 4a plus bx squared plus cx equal to 3x minus 1. And from here, you solve your equations. So you get your a plus b x squared plus cx plus 4a equals 3x minus 1. A plus b is 0, because on this side there is no x squared term. I mean, you can put 1 if you want to. So now you see that ab corresponds to a 0. Then your c is equal to 3, and your 4a is equal to 1, because this is a constant term, and that's the constant term, right? So you have that your a from here is equal to 1/4, which immediately means that b is negative 1/4, so they can add to 0. And here's your ABC, which immediately gives you up here, you have your E solution on the first one, and then you will have your hyperbolic sine and hyperbolic cosine from the second part, because you do have B and C. Now, clearly, if B or C came out to be 0, in that case, right, that part, remember when I split this into 2, then one of those two parts would die, right, if B or C is 0. So partial fraction decomposition will be used, pretty much all the time. In a very, very, very rare, bizarre set of circumstances, right, you can use trigonometric substitution, because that one could also spit out some solutions that would lead you into hyperbolic solutions, because the answer can be inverse tangent, and if you remember, that's connected to that 1 over 1 plus x squared and so on. So, trigonometric, I want to do one more of these partial fraction, but trig sub is another potential thing that can be, kind of didn't even want to put that on the thing here on the review, but then I decided, what the hell, I mean, if it can show up, if it's remotely possible, why not? Let's take a look at one of these problems. For instance, I'm just going to go into Kalk2 textbook and just pick literally anything. I just want something that it's a little bit more colorful. maybe this one would be good. It's not too crazy. I don't need the integral. I'm just working on the decomposition. I'm just working on a decomposition. Okay. This is a repeated linear. And this is just linear. And most of the time, that's exactly what you have. Rarely, you're going to jump into others. So I have a over x plus b over x squared plus c over x plus 1. So that's the setup. I have a linear with a repeated linear, so that's all a repeated linear, and then a single linear, which is x plus 1. And now, all I need to do is to multiply each one of these by what's missing. X plus 1, x plus 1, x squared. Once I multiply with all of these, I have the common denominator of x squared, x plus 1 everywhere, and we are we're good to go. Okay, so when I distribute this x, that becomes x squared, so ax squared plus ax plus bx plus b plus cx squared equals to x minus 5. Now all of these x's in your differential equations will be s's, right? So each one is s, which creates issue when you write s minus 5 and it looks the same, right? So just be careful. You know, your 5s should be boxy, and then s should be all curvy, right? So it doesn't make those problems. All right, so we have a plus c times x squared plus a plus b times x plus b is equal to x minus 5. And this would be what? It would be a plus c is 0 because there is no x squared term. A plus b is going to be 1. That's the coefficient of x. And we just know that b is negative 5. So if b is negative 5, that immediately means that a is 6 and c is negative 6. Because, right, when I plug in negative 5 for b, move it to the other side, 1 plus 5 is 6, so a is 6 and c has to be opposite, so they add to 0. And there I have my 6 over x minus 5 over x squared and minus 6 over x plus 1. And that's my partial fraction decomposition. Now all of these will be your s values, and then the first ones will give you the t solutions, and this one over here would give you the e solution. Right, this one over here is e to the negative 6e to the negative t when you transform it in using the tables. Anyway, that's the partial fraction decomposition, and it's the one that you will be using most of the time. Now, obviously, if you don't know this, which is a setup, right, for the problem, you can't get far. So you have to be careful about that. Yes. Yes. Previous over here somewhere. So if my a is 1/4, a is 1/4. I'm not sure. Oh, yes. Okay, that was wrong. You are correct. So that's a negative quarter, and then b is positive. Yes. B would be positive. Holy nightmare. You are right. Yes. Yep. Did it too quickly. Did it too quickly. All right, good. Good catch. Good catch. All right, now for trigonometric substitution. Now this thing is designed when you, most of the time, right, you have, this thing is designed and most of the time you have square roots and things like of that nature. But you don't always have to have a square root to use trig sub. And this is where this thing could sometimes be useful, right? So if you have integral of 2x over x squared plus this is a basic U sub problem, guys. Basic U sub. All right, this x is gone. It's just 2 over. All right, there we go. Let's put it this way, right? So 2 over x squared plus 1, and now I can use my oh wait, now this is inverse tangent. Basic integral inverse tangent. Here we can fix it like this. There we go. All right, so in this case, right, you can't use inverse tangent. It's no longer a basic integral. And we have, I mean, you can use partial fraction decomposition, right? Because you have a repeated prime, but it's going to give you those four variables, right? So how about the trig sub? Maybe we can solve it quicker with the trig sub. And when you draw the triangle for the trig sub, again, details of this are on the online. And again, don't use this if you are not good with trig identities to do the integration, right? Trigonometric integrals. This is why I was kind of like, should I put this on or should I keep it out? But you know, it might be useful somewhere. So I was just gonna say, you know, let's just have it, because you do see that the form could be something like what you would get in your inverse Laplace. Obviously, this would be an S in that case, and right. So now, when you make your trig functions, I'm gonna get my tangent. No, I'm gonna swap these, because that's gonna give me, if I put x over here and 1, you can put these are both legs because there is a plus in between, so you can put these in any order you want. And then if it's a minus, then, well, I need to explain that from scratch because no one teaches it that way other than me. Okay, fine. A, B, C, and then A is equal to A is equal to C squared minus B squared. And then B is C squared minus A squared. And then C is A squared plus B squared. Right? So these are the three formulas that you can write looking at the Pythagorean theorem. So what you see here is that when you have a plus inside the square root, and you can imagine a square root over here, when you have a plus, then A and B that are given, which are these puppies here, are the legs of the triangle. And this one is the hypotenuse, which you can find as a whole thing, which is exactly what I have. So that's like a side how to set up your trig substitution. Now pretty much everyone else is teaching the formulas, those three formulas, and then you plug the formulas, and then, you know, by the time you're done with Kalk2, you forget the formulas and you can't do it anymore. right? So when it shows up in the later coursework, it's like, I don't remember, those formulas are long gone. Well, if you learn it this way, then you don't have to know the formulas. Because now, what I have here is the tangent theta, if this is theta, is equal to x over 1, from where x is tangent theta, and dx is the derivative derivative of tangent is secant squared theta d theta. And you can also write a cosine function. Cosine theta is equal to 1 over the square root of x squared plus 1, from where the square root of x squared plus 1 is equal to 1 over cosine theta, which is secant theta. And that's exactly what you need, because you want only tangent secant pairs. So now when you look at your substitution, right, you have this piece to plug in, which is secant, and you have this piece, which are the things that you are substituting in your integral. You kick 2 outside, you have now 1 on top, and now the bottom. This is usually confusing for people, I'm not sure why. I need this to be squared, and I have it as a square root. If I want to get the square out of this, I need to raise both sides to the 4th power. Because 4th power is 2 times 2, and you have a square root which is 1/2. That 1, 2 will cancel that half, killing the square root, and the other remaining 2 is matching this one. That's why you are raising both of these to the 4th power. So what you actually have at the end is secant 4 theta, and then instead of dx, you have secant squared theta d theta. And now you see that they nicely cancel. You get 2, 1 over secant squared theta d theta, which is 2 cosine squared theta d theta. So we were able to go from the integral that we cannot integrate at all into something that we can quickly now integrate using the power reducing formula from trig course, right? So you have 2 integral of 1 plus cosine 2 theta over 2 d theta, then these 2's canceled, and so on. So now it becomes a basic problem, and you can solve it. Again, useful, right? Useful in some cases, but it depends on how well you know your trig. And unfortunately, most of you forget it, right? So maybe partial fraction decomposition, even when you have to do, 4 constants, which is, 4 equations and 4 variables, is something that we have to deal with. So it's there, just in case. I'll put the 3 dots here. You can finish the problem, because now it's just basic integration. Oh, actually, wait, no, let's not do that, because I need to bring it back into x values. So I need to integrate 1 plus cosine 2 theta d theta. The integral of that is theta plus the integral of cosine 2 theta over here. Integral of cosine is sine 2 theta over 2, and then we have the plus c. And what you have here is this part is formula again. It's a plus. Sine theta cosine theta over 2 plus c, and then these 2 and 2 drops. Now, solve for theta. Let's go back. We can solve for theta anywhere. Can be inverse tangent of x. So this problem is bad, obviously, because it's not going to be inverse tangent of x for Laplace transform, but a problem could line itself up for something like this. And then you have plus sine theta, you read it from the triangle, which is x over the square root. And then cosine theta was 1 over square root plus c. And when you multiply these roots, the square root cancels, because it will be square root squared, and you get x over x squared plus 1. Oh, wait, right? Wouldn't this be your hyperbolic cosine, right? So these things pop up. Obviously, this part is useless over here. This part will not show up either, and so on. But as I said, the problems sometimes line up, and some of these techniques might be useful. And I'm not talking only about the course you're taking right now, because some of you engineers will be taking tons of these courses. Differential equations will be featured in many of your coursework outside of math, right? You should be taking at least partial differential equations for thermodynamics and a whole bunch of other courses that will use the partial differential equations. But more important for those is the knowledge of power series, which is the last part of our review. I did also say improper integrals, and I did not acknowledge those. I'm sorry. I did talk about them already right here. When you have the infinity as a limit, you swap that infinity with finite value b, and then you send b to infinity in the limit. So that's something that is called improper integral of type 1, also in calculus 2. And it's only used in this setting because you just have this upper infinity limit. Again, that's something that this limit fixes up over here immediately. So we don't have to worry about that too much. It's just, remembering the name of it. So that's the improper integral. Now, the biggest emphasis on tonight, apart from integration by parts and partial fraction decomposition, which are the two main things for Laplace, we have the huge emphasis here, blood red, power series. And we are going to see what we call the power series solution to the differential equation, which is our chapter 8. And the problems for this are not fun by any means. Now, given that we have 5 classes left, we will start our power series probably on Monday, not after Thanksgiving, but the Monday after the week after Thanksgiving, so whatever, 10 days after Thanksgiving, let's put it that way, that Monday. And we'll have one class 8.1, the other class on Wednesday 8.2, and then following Monday is the review for the course, and then followed by the final on Wednesday 2 days later. Only 2 sections on power series. I believe the book has 3 or 4 sections on it. We're only working on first 2, and that's already going to be, enough. Now, let's see what the power series are. So you learned in calculus 2, I believe it was chapter 11, that functions can be represented as the power series, right, infinite power series of Cn coefficients, right, of some kind, and then you have some power x to the n. So this is just what you call centered at x equals 0. And then you can also represent the power series same way, but x minus a to the n, which is centered at x equals a. What is the purpose of this power series? Power series is going to take a function which is, let's say, transcendental function, e to the x, or a sine, cosine, or whatever combination of those, and represent them as infinite polynomials. But then you can chop those infinitely many terms into finite couple of terms, and you will get a very, very good approximation of the e to the x or whatever else. But remember, now it's a polynomial and you can compute it easily, and you can differentiate it easily, and you can integrate easily, which really helps a lot with all of the calculations you guys did in the past. Literally, if you have enough computing power, nullifying all of the calculus you did up to that point, because with this you can make anything into a polynomial, approximated polynomial, and then within whatever margin of error you desire, compute the values and do integration and derivatives and everything else without worrying, right, too much and breaking too much sweat. It's a very, very powerful tool which gives insanely bad results if you don't know how to use it properly. But with this, we will be solving our differential equations in chapter 8. We will assume the solution to be this power series going from 0 to infinity of Cn x to the n. And then we will differentiate it twice and plug in the differential equation and so on. So what I need to review today is the properties of power series, but also derivatives, integrals, and basic power series, so you can recognize them. I do tell to my students in Kalk2 class, here are the 5 that you need to memorize. So when you get to differential equation chapter 8, you are not going crazy. Okay, fine. But there is a little bit more to that. So let's take a look at skills and formulas that we need to survive this. So the first skill and the first formula, procedure is shifting the counter. And this is insanely important. So shifting the counter. Now let's see what that means. See, when you have a power series that starts at, let's say, I equals 0 to 3 of, let's say, Ci as the index, all you get to write here is C0 plus C1 plus C2 plus C3. You don't know what these C's are or whatever. You just have this as the index, and then it gets spilled that way. Another thing for summation, and I mean, you should all know this, but I'm going to write it. Let's say 2 to 5 of, let's say, x to the I. That's going to be x squared plus x cubed plus x to the 4th plus x to the 5, and you stop. Because your top number made it stop. But then you have the summation I goes from 0 to infinity, and then you have your Cn x to the n, which becomes C0 plus C1x plus C2x squared plus C3x cubed plus ... and this going to infinity, infinitely many terms. It's an infinite polynomial. If you carefully look at this, you see it's a polynomial. See your y equal mx plus b? It's right there. This is your mx plus b, right? So it's there. You can also find your quadratic. Your ax squared plus bx plus c is also there. And then the cubic and the quadratic, and right? So all of them are there. That's infinite polynomial. Now, if I am able to somehow write others as polynomials, polynomials are a joke to integrate and differentiate, but see, I need to be able to put all of those together, right? And I'm looking at the counter here. Now, here is the feature and why we have to shift the counter. Sometimes right? You can see that all of these, right, this one started at 0, this one started at 2, this one started at 0. I can add these two, but I cannot add this one to them because it starts at a different number. It starts at 2. It doesn't start at 0 like the other two. So if I want to add I2 to infinity of, I don't know, Ci, plus another summation where I goes from 0 to infinity of di, let's say. These are indexes. Doesn't matter. I can't add these until I have the same value in here. Now, there is something that is called a forward shift and a backward shift. And in some cases, you are stuck to do one or the other. In some cases, you can pick. Now, it's so much easier to match these counters to start at 2 than to start at 0. And let's see what happens and how this is done. See, this one over here, we said it's C2 plus C3 plus C4 plus blah, 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 blah. And this one over here is D0 plus D1 plus D2 plus D3, da, 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 da. They are not starting both at 2. But see, if I peel off these first two terms and write them separately, then my summation will start with the D2. And then the 2 in the counter will match the first one. So if I copy the first series, I starts at 2, infinity of Ci, and then I just peel off D0 and peel off D1 and leave the rest in a summation. Ooh, now they match. And because they match now, I can mush these two series into a single series. And that's what we are after in our differential equation course. When we do 8.1, 8.2, I will only have, in an hour and a half, I will only have time for 2 examples maximum. Each one of those like 30, 40-minute example. Because a lot of calculations. Now, when you are able to peel off terms like this and combine the series, oh yeah, we're good. In that case, right, I have my D0 plus D1, and then plus summation I goes from 2 to infinity, and inside I have Ci plus Di, and you know, these guys are combined into one, which is what I was looking for. But the worst case is if you are not able to peel, you have to shift this one into 0. That's the evil case. And that's the one that you will have to actually do more often. Now, those you were supposed to know how to do this from your geometric series, right, Kalk2. But again, not everyone covers examples like this, so you might have never seen it before. My question now is, how do I move these counters? So the first one is 2 to infinity of Ci. It doesn't matter what you have here. You have some function in terms of I. We don't care what it is. Plus another summation where I starts at 0 to infinity of Di. And you need to add these two series. Now again, I can't peel off 1 and 2 for whatever reason, and we'll see the reasons why when we get to our sections. So here is what you need to do, and hopefully you will refer back to this. You subtract 2 on both sides over here. That creates I minus 2 equals to 0. And then you rename this I minus 2 into, let's say, k. So you have k equal to 0. Now, when you rewrite this series, you will rewrite this as k equals 0 to infinity, but then you have to have ck. You can't have ci. Okay, so how much is I? I is k plus 2. From here, right, your I minus 2 is equal to k, which means that I is k plus 2. So now look at this series, and you see that this entire series now is in terms of k. It starts at 0 where we want to, and you have a k and you have a k. And then you still have plus summation I goes from 0 to infinity di. Well, all I'm going to do now is going to rename this back into I, keeping its form. Right, this is where some people lose their mind. Like you can't just change the name. Yeah, I can, right? I just go to the office and I fill out an application, and tomorrow I'm Samantha. I'm no longer Nick, right? So you can do that in mathematics as well, right? I'm just going to go and change my value k for I. But this is the key, right? You see that the counter changed, the index changed within the problem, within the sum. So now this sum and this sum is the same sum. They have the same, when you compute it, it has the same value. Everything is the same about it. They just look differently, right? Because we shifted the counter and we added, right? We shifted the counter, we added 2 terms, but that actually shifted our CI over there. Now, please recall what is your first value here. Your first value is, when you plug in 2, is C2. Well, what is your first value when you plug in here? Plug in 0, it's C2 again, because C of I plus 2, which is 0 plus 2. So it's the same series. You get in both series C2 plus C3 plus C4, right? That doesn't change, but they're written differently. And the benefit of that is obviously, look, I can now add these two because they start at the same value, go to infinity, and in here I have Ci plus 2 plus Di, and there you go. The goal that we are going to have in our chapter 8 is to add 2 or 3 series together into the same equation. Then we're going to factor some things out and blah 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 to create a recursion equation, and then recurrence equation, and then go from there. So there's going to be, fair amount of these types of calculations. Now you might say, well, why does that arise? Right? Why do we have to bother with this? Well, it's again something that was there in Kalk2, the derivative of power series. You see, when you have a power series, let's say y f of x, whatever, is equal to summation 0 to infinity of cn x to the n, and you take the derivative of that thing, what you get is now the y prime is equal to summation I starts at 1, and there we go, and you got your cn n x to the n minus 1. You see that there's no difference in the derivative. Derivative is still basic Kalk1 derivative. Copy the constant, which is cn, and then the derivative x to the n is n x n minus 1. No difference there. Except, it doesn't match anymore. And then if you have to find another derivative, then, yeah, exactly, right? So what do you think this does to a differential equation that looks like this? Let's say. Well, of course, you're going to take all of this and stuff them in there, and then you need to add them. But look at the counters, right? And now that's a problem. So you have to shift the counters so they all fit. Now, luckily, when you shift the counters to fit, these will immediately fix. And then everything will click together and it will work great. But again, these are the things for us to learn in differential equations. So I'm not going to do that now because that's what our class is. But what you see right now on the screen is your calculus 2 basic property of derivatives of power series. I'm not even going to go into integration because we don't need it. So I'm not going to write integrals for it, which is also the part of Kalk2 lecture. I believe that's like 11.4 or whatever the hell it is. But the derivatives are the ones that are going to show in our class in 8.1 and 8.2, and you need to be able to find those derivatives and then stuff them into the differential equation, and then good luck after that, right? Another 2 pages of merciless calculations. It's the most powerful method to solve differential equations, but it comes at a price that it's absolute pain to compute it. And you have to match these coefficients then, right? Counters, so that you can go and deal with all of these things. So that's the story on like very, very basic power series, right? And we still need to talk about the power series that you need to know so that you can recognize them within the problem and use them to kind of unveil the equation. It's like almost like inverse Laplace, because when you solve these power series questions, you're going to get that your answer is going to be y of t equals, and then you're going to get some whole bunch of terms. Are you able to put those bunch of terms back into summation and then look at the chart or in your brain, right, the power series, and write what function they make? So I suggested to my students, I always suggest to memorize the 5 power series, which are very frequently solutions in some way, right, to the problem, and that is obviously the most important. Here, let's go blood red over here. E to the x, which is the which is the summation of x to the n over n factorial from 0 to infinity. Now, if you want to write it out as this is the important bit. But again, you need to be able to write this as a polynomial of 1 plus x squared over 2 factorial, which is 2, plus x cubed over 3 factorial, which is 6, plus, right? So when you look at this, your power series might spit out something like that. I mean, this is what the answers look like. Then you jump here, then you jump here, because you know what this is. And how many cases you are going to have your solution to be e to the negative 2t. Right? Well, that is going to have the form, except all the x's are t's and right, all that kind of stuff. So you're going to have this solution pop up many times. Then I said sine, cosine, and sine hyperbolic and cosine hyperbolic. That's 4 formulas, but they all mush together to create that. So technically you only need to remember 2, and then the other ones, the other 2 are easy. So sine x is equal to summation 0 to infinity, and then you have x to the 2n minus 1 divided by, I forgot the alternating term. Hold on. Negative 1 to the n. There we go. And then you have the x to the 2n minus 1 over 2n minus 1 factorial. So this would be your sine. And it's plus 1. You know why? Because when I started 0, if I started 1, it's a minus 1. If I started 0, it's plus 1. Because when I plug in 0, then 2n is 0, so the exponent is 1. If I have it as a minus 1, when I plug in 0, the first term would be x to the minus 1, and that's not good. All right, so what do we see here? We see x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus dot 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 going forever. When you catch a glimpse of this type of the power series, you know it's sine x, because that would collapse into this, and then this equals to that, which is technically, right, what you have. Now, a cosine one is 0 to infinity, negative 1 to the n, right? And then now you have x to the 2n over 2n factorial, and that's going to be 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 factorial plus dot 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 going forever. Can anyone make an interesting observation regarding sine and cosine? Looking at the polynomials over here, what do you see? Excellent. Exactly. Do we now understand why sine is the odd function and cosine is the even function? You were asked to memorize that in pre-calculus. You were asked to memorize that feature. And you drag that with you all the way to Kalk2. I'm not sure if this was pointed out to you in Kalk2, but there's why. Your sine is odd and your cosine is even function. So now that ties a couple of things together. Now guys, look at the hyperbolics. You have your sine hyperbolic x is the same formula, it just doesn't have the alternating term. We take out alternation for sine hyperbolic. We just take this out and becomes sine hyperbolic. It's the same string, it's just all pluses. X to the 5 over 5 factorial plus x to the 7 over 7 factorial plus dot dot dot. And the same obviously for cosine hyperbolic. Cosine hyperbolic x is equal to summation 0 to infinity, and over here you have x to the 2n, which are the even powers now, and 2n factorial, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. No, lies. It's supposed to be a 4. There we go. X to the 6 factorial plus dot dot dot. Do you guys see something interesting now? And do we remember the formula? That's how it is all connected. Like every single part of mathematics you ever learned, right, has to click from every possible angle. No matter which way you look at it, it has to click together, right? So if I am to take this top one over here, right, and make and make a negative e to the negative x, well, that's just going to give me minus signs on each one of these. So I'm going to get 1 minus x plus x squared over 2 factorial, because minus was killed by a negative, but the next one is minus x cubed over 3 factorial, and then plus x to the 4th killed the minus, and so on factorial. And then when you add them together, 1 plus 1 makes 2, but when you divide by these 2, it goes back to 1, and it matches your 1 right there. And it goes like that. So those of you that are, more motivated to learn these connections in mathematics, you actually sit and play with this. You put these formulas together and you grind through, writing all of this out, just to show to yourself that these actually are the formulas that all fit together, and they get us right where we want to be. All right. I think we talked about the derivative. We put down, oh, I forgot the inverse tangent. Holy nightmare. I forgot the inverse tangent power series, right? And what do we know about the inverse tangent? Well, inverse tangent is also an odd function. So that helps you actually memorize the inverse tangent situation. That's negative 1 to the n, like the same as before. And then you have, just like sine, you have x to the 2n plus 1 divided by 2n plus 1. But guys, you do not have now the factorial on the bottom. You don't have the factorial. You just have this. And that's your tangent inverse. It's very, very important creature, because it does show up. So that will be x minus, and then we have a cube, so over 3 plus, because of the alternation, x to the 5 over 5, again, no factorial, minus x to the 7 over 7, no factorial, plus going on forever. So anytime you have this alternating term, you have your sign go plus, minus, plus, minus, plus, minus, plus, minus. That's why it's called the alternation term. And then you have whatever is in there to make what these guys would look like individually. And you achieve that just by placing, right? First time around, you plug in 0 in the whole thing. That's negative 1 to the 0, x times 0 plus 1 over 0 plus 1. And when you compute all of that, you get 1, and then you get x to the first power and 1. So the whole thing is x, and that's how you got your first term when you compute all of this. Then the next time around, the counter becomes 1. When you plug in 1 everywhere, well, that's going to keep this thing. And when you plug in, this power becomes 3, and this number becomes 3, and you get your next term. And it's negative because of negative 1 to the first power gives you negative 1 to multiply by, which makes the second term negative. And you can keep going like that until you see the pattern. So the power series are going to nicely differentiate, and then nice to integrate as well. And a little bit of the pain in the neck when we have to add them and subtract them, because we have to match that counter. Without matching the counter on the bottom to start at the same location, you can't combine two series into one series. And yeah, that is pretty much what I wanted to say about these things. I gave you the list of power series that will save your life, especially to the x on top and the trig ones. Now the hyperbolic ones do show up, but again, they're competing with the E because it's the same universe of solutions. Oh, by the way, when I learned differential equations for the first time, well, when I learned differential equations, not for the first time, I just learned it. I didn't learn it second and third time. I just learned it once. When I learned differential equations back in a day, my solutions were either hyperbolic or trig. Like, we never used e to negative 3t, and so very rarely, actually, very rarely. Because we had these two worlds, two opposing worlds, the worlds of hyperbolics, which include those e's inside, and the world of trig. And you put those together and you have your answer. And then you learn through that your oscillating systems, like alternating currents in circuits and spring systems in mechanical engineering, are the ones that will always have sine and cosine solutions, where other systems that are not oscillating will have hyperbolic solutions, which you can convert into your e's, right, if you care about e's more. But it's very interesting to see that, trig and hyperbolics actually split the world of solutions in half, right? Each one claiming its own type of a problem. I mean, both bags have infinitely many problems, obviously, but yeah. Questions, concerns, literally anything that you might have regarding Kalk2 review. I guess there will be a no, so we're going to say goodbye to YouTube.